in this, well, I guess not really solution, but properties of liquids. And we started talking about some intermolecular forces. So remember that intermolecular forces are those forces that basically hold together one entire molecule with another. And that's not to be confused with, as we also talked about, intramolecular forces. Intramolecular forces are the forces within a single molecule that holds it together. So you can kind of think of those almost like the ionic bonding, covalent bonding, sharing of electrons, or sort of the electrostatic attraction between a positive and negative ion. And those are really, really strong forces, the intramolecular forces, as we talked about. And intermolecular forces, which are those forces between individual molecules, are much weaker than those. And that's why, again, as we talked about, when you go and sort of boil water, it doesn't completely fall apart, right? So all the hydrogens and oxygens don't break apart from each other. What the first thing that happens is the entire water unit in liquid water breaks apart from another water unit in liquid water. And obviously it goes into the gas phase. And obviously we get basically steam or water vapor that's basically made. There are a few different types of intermolecular forces that we talked about. We talked about dipole-dipole interaction, and that's really the uh, intermolecular force between polar molecules that do not have the ability to really hydrogen bond. Um, now, there's also hydrogen bonding, which is really a special type of dipole-dipole interaction. It's a relatively strong intermolecular force. It occurs between a bond between hydrogen and nitrogen, oxygen, or fluorine, which is, again, is our three sort of high electronegativity sort of elements. And lastly, there's sort of dispersion forces, which, as we talked about, are really these sort of temporary weak type forces that occur. And they're the sort of weakest because they sort of need something to occur in order for them to interact with each other. Electrons maybe either kind of going one side of the molecule or the other. That polarizability we talked about are, again, an induced type of dipole to occur. And again, they're temporary. They really don't have a long way to continue those interactions with one another. So in terms of strength, our hydrogen bonding, which is really for polar molecules that have the ability to hydrogen bond, is the strongest. Our dipole-dipole is sort of in the middle, next kind of strongest. And the weakest out of all of them, again, would be those dispersion forces. And they affect things like boiling points, melting points. So sort of the stronger we have in terms of those intermolecular forces, the higher boiling point, melting points we would expect. And obviously, the weaker those forces, the lower of those melting and boiling points we would expect. We then started talking about some other properties of liquids. We talked about adhesive, cohesive type properties and why we sort of get our sort of meniscus that we typically see. We talked about vapor pressure, which again is sort of the gas above a liquid. Obviously, that gas causing pressure occurring above that liquid. So I think where we left off was here, which was sort of touching upon here boiling. So let's talk a little bit about boiling and sort of what is happening when we get to the boiling. Boiling obviously occurs at the boiling point temperature, for example, and for water, that's again like 100 degrees Celsius. And when we get to the boiling point, we're really starting to add a lot of energy, usually in this case, enough energy that allows really those sort of molecules in the liquid phase to escape and really get to the surface and kind of go out from the liquid part into the gas phase. And if you've obviously ever heated a beaker of water or something of water, even a pot of water there, when you kind of first put it up there on the the fire, you sometimes will see a lot of like bubbles. I don't know, I guess we shouldn't call them bubbles, but bubble looking things. They're very, very small guys. And sometimes people think, oh, wow, it's starting to boil already. And it's really not. What you're actually seeing is actually a lot of the CO2 coming out of the water. And it becomes less soluble as you hit it with that heat really quickly. And that's sort of what you're sort of seeing at that point. It's not really obviously until you kind of see sort of real bubbles, if you will. really big bubbles, right? Kind of working their way from the bottom to the top, that they are essentially um, boiling at that point. You also will notice probably if you watch it at some point, maybe when you're first starting the process, you'll get some bubbles that maybe will kind of pop, if you will, before it kind of gets to the top. And that's because inside really these bubbles, right, is basically water vapor or gas. And it's not really until, the pressure inside those bubbles is equal to or sort of greater than the atmospheric pressure, because don't forget we got kind of atmospheric pressure pushing back down on it. So before that, they start to pop, but at some point they will reach that point and we will get those kind of bubbles to get to the surface. Once they get to the surface, obviously at that point, they're going to pop, going to release, right? Our steam that we see as basically our version of water in the gas phase. Now, at what temperature something boils does depend both on temperature and pressure, which we'll talk a little bit about. There's, certain pressure temperature relationships that sort of need to be reached, for boiling to sort of occur. Playing with the pressure, for example, you could actually get things to boil at a very, very low temperature. And obviously, raising the pressure would affect the boiling point as well. So, pressure, temperature, and boiling point, they all really play a key role. And we'll see some of the what are sometimes referred to as phase diagrams a little bit later on. But they do have an effect, obviously, on the boiling point. Raising the pressure does increase the boiling point. Again, with the lid on, like a pressure cooker here, we're getting a lot of that sort of condensation sort of happening as we start heating. We got a lot of that vapor pressure above the liquid, going to cause this liquid here to actually boil at a higher temperature. So we will get that sort of, I guess, stuff we're cooking in there to cook a little bit faster, maybe in that sense. Again, it's going to be cooking a little bit at a higher temperature than it would if we obviously didn't have such pressure sort of involved there. Opposite of that is true as well. Obviously, if we lower the pressure, we will sort of decrease the boiling point in that particular case. Now, when we're talking about boiling, sometimes people sort of see this sentence and think it's kind of a weird thing. And boiling is actually a sort of cooling process that's occurring. And it may not seem that way, but it actually is. And when things start to boil, is cooled as fast as is heated by the heating source on the bottom here. So as we start heating this, we're gaining a lot of obviously boiling to occur. And the result of this is that heating from the bottom and cooling from the top is sort of where we get that 100 degrees Celsius. And sometimes people are you sometimes concerned in person when they put a thermometer in, they look at their thermometer into some boiling water and like it kind of maxes out over there like 100 degrees Celsius, give or take. And they're worried, well, it's boiling. Is it going to continue to rise and break my thermometer, sort of the temperature that happens there. And it's really not because of this, because basically as we're heating from the bottom, kind of inputting energy, we're getting all these fast moving molecules that are basically breaking themselves out into the sort of environment there. And now we got kind of a net release of the energy out the top. So we're kind of heating from the bottom, releasing that energy out from the top. And what it does is it sort of is able to basically maintain its boiling point there at 100 degrees Celsius. Give or take how the pressure is, it probably won't necessarily be exactly 100 degrees Celsius, but in an ideal pressure situation, we would expect it to kind of stay there. So although, we think about boiling as sort of a heating sort of process, it actually is a cooling process. Again, we're removing a lot of those molecules from the solution, kind of lowers the overall energy of the solution. And those guys that are escaping the solution are now kind of moving perhaps a little bit slower as well, kind of lowers the overall energy of the environment because it takes a lot of energy to kind of get themselves out of the liquid part. Now, when we talk about liquid and sort of the gas phase, another process when we get to sort of the boiling point, right, is what is known as evaporation. And that is obviously going from liquid to gas sort of conversion. We see that as an endothermic process. So remember endothermic when we talk about delta H, which is the enthalpy, and that's sort of the heat of a reaction. That usually would result in a positive delta H value. Condensation, on the other hand, is sort of the opposite approach, but endothermic does mean that heat and energy is absorbed, basically, right? So if you just think about water in that picture we just saw, you had to put fire underneath it, right? So you're adding heat and energy to liquid water to get it to go into the gas phase. Condensation, which is basically the opposite move there, going from gas back to liquid, that is an exothermic process, which means the delta H value is typically negative, and that means that heat and energy is released in this case. So through the process of condensation, all these really fast moving sort of gas molecules is going to release energy. And then obviously you start to move a lot slower. And at some point, they really won't have enough energy to escape each other. They'll start kind of sticking to each other. And before you know it, they'll kind of drop into basically the liquid state at that point. So as it gives off that energy, they no longer have enough energy really to sustain keeping away from each other. And that's obviously different than what happens here in vaporization. When you keep putting that energy in, they actually do have enough energy to kind of keep away from each other and moving around, and they don't really start to stick to each other. At the surface of water, as we might have talked about the other day, we really do have this sort of constantly happening. We got some guys that are able to sort of escape the liquid into the gas phase. Then you got some slow moving gas molecules that are just going to kind of come back the other way. So there is sort of a rate of evaporation and a rate of condensation that occurs. Obviously, this all occurs at the boiling point. And, for something like water, that's 100 degrees Celsius, right, where that occurs. And both of those processes, both evaporation and condensation, basically occur at exactly 100 degrees Celsius. So, as I mentioned before, in that process of sort of boiling, the liquid molecules basically escape that phase and they take a lot of their energy with it. So, when we look at this sort of boiling water bath here, as it's starting to boil and we got all those steam sort of happening, we're losing a lot of energy coming out of the liquid part of basically the solution, even though we're heating it from the bottom. And as those guys sort of escape, they're now going to be moving in the air here a lot slower than, say, air molecules. So overall, it's actually cooling down, like I mentioned before, sort of the surrounding air, if you will. So overall, boiling in that sense is really a sort of cooling process, even though it's sort of, we think about it kind of backwards in that sense. So we think about it as we're heating it, we're adding energy and that type of stuff. So we're increasing the energy. We don't kind of think of it in that terms a lot of times as sort of a cooling process, but it really is that sort of situation that's occurring. Any questions on that there? So then let's talk a little bit about evaporation and sort of what's going on with that. Evaporation, as the water cools, the evaporation rate starts to decrease, and we can maintain basically this evaporation rate when it comes in contact with your skin, like a warm surface. And that's why, again, when we have sort of water, for example, on our skin, it actually increases the rate of evaporation of the water. And that's a really bad drawing of a hand, but we got some water here on our skin. The rate of evaporation will really start to increase. And where's all that heat and energy coming from? The heat and energy is really coming from your hand, right? Or your arm, whatever the water may be. And that makes you feel cold in that case, right? That's also why we start to sweat, right? When we're kind of overheating. And that's our body's way of basically making this process occur. We put some water on our skin. The water on our skin is going to increase the rate of evaporation. Increasing the rate of evaporation is going to kind of pull the heat and energy out of our body, thus sort of cooling us down So evaporation here being sort of a cooling process as we sort of have that evaporation occur. Now, condensation is sort of the opposite. Condensation is really a sort of warming process. So if you think about what we were just talking about with sort of condensation, is when we're going from gas back to liquid, that's going to be an exothermic type process, which means heat and energy is released. So, for example, when you're maybe taking a shower or something like that, and it's like hot water, there's a lot of steam everywhere. You can see some condensation sort of happening on the mirror and all that good stuff. During the process of when you're sort of taking the shower and so forth, and it's warm water, you really don't feel cold, right? Even though you're kind of being hit with water, right? And if you think about it, we have a lot of condensation occurring because there's a lot of liquid around. And what's going to happen is, I'm sorry, a lot of kind of steam happening from the hot water. So there's a lot of steam that's going to start to go through condensation, and that gas is going to go back to the liquid. All the heat and energy that's being released by that sort of steam that's coming out of the water is going to hit something, and it's going to hit you in your body, right? Because you're standing there. So you're picking up all that heat and energy that's basically coming off, from the steam from the water. That's also why when you're done with, say, the shower and you shut off the water and kind of the steam subsides and you have water on your skin, then you start to feel cold pretty quickly. And again, because you just kind of flip the switch there from going from a lot of condensation, a lot of heat and energy being released in the room to now I have a lot of water on me, a lot of evaporation is going to occur, and I'm starting to again start to feel cold as we do that. So condensation occurs as slow moving water molecules basically collide, stick together. They drop back into basically the liquid. And when we do that, fast moving water vapor tend to bounce off one another at the surface. Then when the slow moving water molecules condense into the liquid phase, hydrogen bonds are being made, which means energy is being released in that case, right? So when we start making bonds, we have to release energy to do that. And that's all a warming process. So as those guys are moving around, and they start to sort of stick together and drop in terms of the environment here, we're moving all those slower moving gas molecules out of the surrounding, increasing sort of the energy. We're starting to then re-hook up, for example, our water molecules with one another, making these hydrogen bonds here are going to release energy and also warm up sort of the sort of solution as well. So again, condensation more of a warming type process in that aspect, because we're kind of increasing what's going on in the surrounding air and also increasing and releasing a lot of energy in the sort of solution as well. Any questions on that there? So a couple of things about sort of phase changes in energy. And again, we don't deal a lot of energy. You'll probably see it maybe next semester as well. But these are what I know as the delta H of vaporization, delta H of condensation. The delta H of vaporization is basically the energy that's needed to do the phase change between liquid and gas, or vice versa, basically. So going in both directions, by the way. So going from liquid to gas or gas to liquid, regardless sort of which way you're going, sort of the heat of vaporization. Now, because these transitions, for example, occur at the same temperature. So for example, something like water, the transition between liquid and gas occurs exactly at 100 degrees. At exactly 100 degrees, we basically have both phases in what's known as equilibrium with each other. There's some liquid, there's some gas, not until you get a little bit above 100 degrees, you get really gas, not until you get a little bit below 100 degrees, you get liquid. But right at 100 degrees is sort of where that transition occurs. And it's the same amount of energy, regardless of sort of which way you're going. It's just described differently in terms of the sign. So as we go from liquid to gas, that's an endothermic process, which means it would be positive 40.7 kilojoules per mole. for water. That's roughly 2,260 joules per gram, give or take. If we were going sort of in the opposite direction, going from gas back to liquid, that is condensation, that would be an exothermic process. And also specifically for water, it'd be minus 40.7 kilojoules per mole. Also the same sort of conversion there, minus 2260 joules per gram. This number, as we will see, is a relatively large number compared to the transition that occurs when you go from solid to liquid. And the reason for that is as we go from solid to liquid, as we will see the number, I think a little bit later on here, it's a much smaller number. When we go from solid to liquid, everybody's still relatively close to one another. There's still some room for movement, but they're relatively near each other. But when we do this transition, as we go from liquid to gas, pretty much everybody has broken apart from one another to get into the gas phase. So they're flying around, or vice versa, they're flying around a lot and then they're coming back together. So it takes a lot more energy either to be absorbed or released to do the transition between liquid and gas than it does to do it between solid and liquid. Any questions on that? And by the way, the heat of vaporization, as I mentioned, does change with the substance that you're dealing with. And also, it's important to remember that if you're not dealing with water, sometimes people always have sort of that 100 degrees in their head. If you're not dealing with water, the boiling point obviously is not always 100 degrees Celsius. Again, that's usually used a lot, but is also very specific for obviously water as the example. I think we kind of covered this here just a second ago, but again, the idea with the shower there, in the hot shower, a lot of steam going through condensation, your body picks up all that energy. When we're done with sort of the steam and we just have sort of water in our body, we get an increased rate of evaporation and we feel cold. While in the case with the steam, we got an increased rate of condensation and we feel a little bit warm in that case. The other sort of transitions that are of importance as well is melting and freezing. Melting and freezing, again, is obviously when we're going from solid to liquid, which is melting, and going the opposite way, liquid back to solid, that is freezing. This also occurs at the exact same temperature. And for water, for example, it is 0 degrees Celsius, basically, where that occurs. And just like sort of at the other phase change, again, that's occurring exactly at, for example, 0 degrees for water. And just like that before, not until you get above 0 degrees that you're really into liquid, not to a little bit below 0 degrees that you're in solid. Right at 0 degrees, again, you have really both phases occurring at the same time, sort of referred to sometimes as like ice crystals. So you got some, ice, you got some liquid water happening right there at 0 degrees. And there is also, like we talked about with the other one, there is a certain amount of energy required just to do this transition. And that is what is sometimes referred to as the delta H of fusion. And that is the energy required, again, to do nothing more than to take a substance from solid to liquid, or to take it in the opposite direction, liquid to solid, not changing the temperature or anything like that, but simply to do the phase change. It's roughly like 6.0, I'm going to go 4, give or take, kilojoules per mole for water. And again, if you compare that to what we just saw there for the vaporization, which was 40.7, it's a very big difference. Roughly, it's about 333 joules per gram is the heat of fusion for water. And if you remember, the other one was about 2,260 joules per gram, which is, again, about, 7-ish times amount of energy to do that transition. Again, you can see it takes a lot less because really, as we go from, solid, where they're packed in pretty tight to each other, to liquid, they're still relatively packed in pretty tight to each other. Not a lot of movement, but again, as we go from solid to liquid, but making this transition that we just talked about, they're completely broken apart from each other. So again, it takes always a lot more energy to do that transition than it does to do this transition in either direction. So to get water at 0 degrees Celsius to form ice, we do need to release the energy. And again, that's going to be exothermic. And we need to apply energy, which would be endothermic when we want to go from, again, sort of solid to liquid in this case. By the way, this is water. And as we talked about a little bit before, and might say it a little bit more, when water is in the solid state, it creates all this open space between the water molecules. And that's why the density, for example, of ice or solid water is a lot less than the density of liquid water, like what we have over here, where these guys can get a lot closer to one another. Again, density is mass divided by volume. Here we create a lot of these open spaces, which increases the volume part of the density equation and decreases the density part of the formula there for ice. The last sort of transitions that we oftentimes talk about is actually going from solid directly to gas, sort of skipping the liquid cleanup part of it, and also going in the opposite way. So going directly from solid to gas, again, skipping the whole liquid situation there. That is what is known as sublimation. Heading backwards, gas, again, skipping the liquid part and ending up as a solid is what's known as deposition. So, for example, dry ice is an example of sublimation. Dry ice is really not ice. It is CO2. CO2 goes from solid directly to CO2 gas, no liquid cleanup, very, very cold as well, right? You can burn yourself, obviously, if you touch it. A process of deposition, there used to have things called CDs and DVDs, and if you looked at those things, they're very shiny. And that's sort of how they get the metals on those guys, or used to get the metals on them. I guess they still do those processes, as through a deposition where they kind of cool it back down and it goes directly from sort of gas into solid, kind of creates this coating up on those DVDs or CDs. So you could go Google what a DVD or CD is if you're not familiar. Hopefully you are, I suppose. I'm not that old yet, I hope. Don't answer that in case I am. All right. So again, as we talked about the molar heat of fusion, that is about, I was close, 6.02. It was pretty close. Like I said before, it's about 333, 335, depending on sort of the number that you use. But again, that is the heat required to do those phase transitions. Again, we don't really do a lot of energy in here, but when you get to, for example, 200B, you'll talk about things like specific heat, and maybe you remember that from the pre-class here before this one. You probably covered specific heat and stuff like that. So these guys are sometimes used with specific heat. Specific heat is basically this equation, Q is equal to MS delta T. That is the heat or energy. That is the mass of a substance. That is the specific heat capacity. So for example, water is 1 calorie per gram per degree Celsius, or 4.184 joules per gram per degree Celsius. So maybe if you learned about that, those numbers might look familiar to you. That's the change in temperature, which is basically final temperature minus initial temperature. It's actually one temperature thing in chemistry that we actually keep in degrees Celsius. But we use something like specific heat, for example, since we're talking about sort of phase changes and stuff like that, we use something like specific heat actually when we don't change the phase. So we use specific heat to calculate the energy when we go from like something that is liquid to liquid state, but we actually change the temperature like 5 degrees to like 25 degrees Celsius. So we use something like specific heat to calculate the energy required to do that transition. And when we would get to a transition of actually going, say, from liquid to gas, then that's where the heat of vaporization would kick in. If we did a transition where we went from solid to liquid, that's where the heat of fusion would kick in. But if we happen to stay in all solid, we would use specific heat. If we were in all gas, we would use specific heat. And if we were in sort of all liquid, we would use specific heat. Again, as long as the phase doesn't change, but the temperature does, specific heat is typically the one you do it. We do Q, works the same way as delta H and energy and all that. Basically, if it's negative, it's an exothermic process. And if Q, which is heat or energy, is positive, it's an endothermic process. And really under constant pressure, as you'll probably learn next semester as well, Q basically will equal the enthalpy of a reaction. So you could do almost a very simple sort of experiment to figure out how much energy is being given off in a reaction. So simple, you could use basically some coffee cups and a thermometer, and you basically can figure out how much energy is being sort of either absorbed or given off in a particular reaction using something like specific heat. This is a heating and cooling curve, and it also illustrates some of the points where we would maybe use something along the way and use something else to calculate the energy. But basically here, in those spots that we see that are the transition spots between phases, and we see right here at 0 degrees, that's our transition there to go from solid, which is like ice, to liquid water. At 100 degrees, if we come up here, that's our transition to go from liquid to gas. So those are our transition points. You can see they are represented by flat lines or plateaued lines, and that's because this occurs at the same temperature. This is basically where we can go from liquid to gas or gas back to liquid, and that is where we would use that delta H of vaporization we were talking about. This is where we would go from solid to liquid or liquid to solid, and that's where we would use our delta H of fusion in this particular case. Now, if you look at sort of the other lines that we see on this sort of graph here, this line right here, if I can find it, there we go. This line right there, this line kind of going up this way. It was sort of straight before I scribbled on it. And also this kind of vertical-ish line as well. What each of those lines basically have in common is they are changing the temperature, which is why the line is basically going upwards. But the phase is the same. So for example, all the way from like here, all the way around here, that is all the liquid phase. So the phase doesn't change all the way through there, but again, the temperature does. And that would be a case where we would use, again, that more specific heat equation to figure out the energy that's happening there. And same thing here. Again, this is all gas phase all the way through there. We would use our specific heat equation to figure out the heat and energy, and all through here, we would use our specific heat equation to figure out the energy that's happening. So for example, if we started way down here and ended way up here, we would actually do each of these steps separately. The first thing that would happen is you go from like minus 20 degrees to 0, and that would be all ice. And you would use specific heat to figure out how much energy just to do that transition. Then what would happen at 0 degrees is you go from 0 degrees ice to 0 degrees liquid water. You would then use your heat of fusion. You then would go from 0 degrees liquid water all the way up to 100 degrees liquid water. That again would be our specific heat. You then would have to do a phase change coming here at 100 degrees Celsius, going from liquid water to gas. That would be our heat of vaporization. And lastly, we would be in the gas phase going all the way up this way. We would use the specific heat to figure out the energy required. If we want to know the total amount of energy to go all the way from the bottom to the top, we basically would just add them all together. So all these individual steps, in my example here, going all the way across this curve, there would be 1 step that would occur, 2 steps that would occur, 3 steps that would occur, 4 steps that would occur, and 5 steps that would occur. You'd find the energy for each of those 5 steps and basically kind of add them together and get the total amount of energy. Good news is we don't do heat and energy like that in this class, so you don't have to worry about the calculation part of it. Any questions about sort of phase changes, energy associated with those phase changes? Okay, so speaking of phase changes, there are certain things that help us decide sort of what's going on, are really, what sort of pressure temperature relationships that we would need, for example, for something to be in the liquid state or something to be in the gas state or solid state. And these are what are referred to as phase diagrams. They have the three phases. So our three phases are solid, liquid, and gas. They also have the 6 inner conversions between them. What are the 6 inner conversions? 6 inner conversions are when you go from solid to liquid, that is melting. When you go from liquid to solid, that is freezing. That is 2. When you go from liquid to gas, that's evaporation. Go from gas to liquid, that's condensation. That's 4. And when you go from solid to gas, skipping liquid, that's sublimation, which is 5, and gas back to solid, skipping the liquid again, that is deposition. So this is what it means by the 6 inner conversions as they go between them. There's also, as we will see on sort of this diagram here in just a second, there is a spot which is referred to as the triple point, and that is really the pressure temperature relationship where your substance basically will be in all 3 phases at once. That substance will be a solid, a liquid, and a gas, all sort of happening at once. So again, that's what's referred to as sort of the triple point area. Water, as we'll see, sort of has an unusual melting point line, a negative slope, and again, it accounts for why we see ice being less dense than liquid water. There are certain parts on this diagram which are important. Let's talk just a little bit about some of these, and that is there is the critical point, it's sometimes referred to. The critical point is where you find the critical temperature. The critical temperature is basically the temperature above where there's real no distinction between liquid and gas or vapor phases. It's kind of the area where you hit this certain temperature and your substance, kind of has some properties that are very much like a liquid, but also has properties that are very much like a gas, like it kind of flows like a gas. So it's kind of no distinction between where sort of gas and liquid sort of vary, or one starts and one ends. And that's also accompanied by a particular pressure at that point. So there's kind of a critical temperature and pressure, which is essentially the critical point. And that also, again, there's real no distinction between the liquid and the vapor phases. In that area where we're at, kind of at that point where we have that critical point in that area, that is what is sometimes referred to as a supercritical fluid. And that is, again, one where above a particular critical temperature, your substance has basically the density of a liquid, but it will kind of flow really like a gas. So that's a certain area that we kind of look at on a curve. So let's take a look at sort of a generic phase diagram just to kind of show you what one looks like here. So here's a generic sort of phase diagram. There's these 3 states. So we have solid usually on the left, liquid somewhere there in the middle, and gas to the right as we go here. We have a line that separates between the solid and the liquid, and that is our melting point line. And melting would obviously be going across that point, and freezing would be going across the other. This line coming this way is between liquid and gas, and that's where vaporization and condensation occurs. And if we come down here below, this is really going from solid to gas, no liquid in between. And that's where sublimation and deposition occurs. Where does this normally occur if we wanted to kind of hone in on the temperature on the X, pressure on the Y? We would look for 1 atmosphere, right? 1 atmosphere is sort of normal pressure. By the way, normal standard pressure and temperature, is really sort of 1 atmosphere, and our standard conditions, I guess, is a better way of wording that. And kind of 25 degrees Celsius is sort of normal sort of things. So, we could say if that's 1 atmosphere, we would go down and figure out what the temperature would be at that point. We do see a couple of things here. We do see our triple point. So again, that is the pressure temperature combination. If I was able to draw straight lines there, where all 3 phases are essentially happening at once, that is where we have something that's in the solid, liquid, and gas phase. Over here is our critical point, where if we again go kind of across, that would be our critical temperature. And obviously, if we go down straightish, ideally, that would be our critical sort of temperature that occurs. And above that point right there, you can see there's really nothing there. So it just sort of flows from liquid into sort of the gas phase. And that's where we find our sort of supercritical fluid that's occurring. So you do need to know what a phase diagram looks like. You need to know where solid, liquid, and gas is. You need to know where you would kind of put the melting, freezing, vaporization, condensation, sublimation, deposition. You know where the triple point would be, pretty much where all 3 of those phases come together, and where the critical point is and supercritical fluid would be. Any questions on that? So let's take a look at a phase diagram. This is for actually carbon dioxide, which is our dry ice. And if we look at carbon dioxide, we see a couple of things. First off, if we think about what we were talking about with dry ice, that, it pretty much goes directly from solid to gas. No liquid is happening in that situation. So why is that? So as I mentioned before, if we look at its sort of phase diagram, we see that under normal pressure conditions, so remember, under normal pressure conditions, we're kind of looking at really 1 atmosphere. So if we kind of go to the chart here at 1 atmosphere, and where's our normal sort of temperature, right? If it starts really cold, right, because dry ice is really cold, but once it gets exposed to room temperature, it starts warming up, right? So as it starts warming up to maybe room temperature-ish, we're there. And you can see that we basically started in solid, and we went straight across from the solid into the gas. And that's why when we deal with something like dry ice under normal pressure conditions and normal conditions, it will go directly from, obviously, as I mentioned there, solid into gas. And you can see at no point under those normal pressure conditions does it actually hit the liquid sort of aspect. So what would we have to do to get it into a liquid sort of condition? Well, according to this phase diagram, liquid is like in this area per se. So we know the pressure here is 5.1 atmospheres. Pressure here is 72.8. So I'm assuming we got to at least get the pressure above 5.1, below maybe 72.8. And, if we keep it kind of in that pressure range and we kind of increase the temperature, we will see basically that dry ice go from solid and then actually get to liquid when it comes to about this temperature. But if we continue through, if we get ourselves then into kind of normal temperature, we will see sort of the gas phase occur. That's, at least 5 to 6 times normal pressure, which usually doesn't occur, which is why we have to really get into some pretty good pressure there to actually try to see it into the liquid phase. Or again, the pressure temperature combination, we got to kind of get it to get it into that liquid phase. So you can use these phase diagrams to, sort of figure out those type of things. What combination would you need to get it into a certain phase? What phase would it be in a certain pressure temperature combination? This would be sort of the critical point, and again, our supercritical fluid would sort of happen past that point. Any questions on that there? So if we look at this phase diagram and try to figure out a couple of things, let's try to figure out in each of these situations sort of what phases or phase will be present. So let's take a look first off. If we started at 20 degrees Celsius And we had a pressure of 72.9. So I got 72.9. 20 degrees Celsius would probably, over here is 31. So 20 degrees would be back a little bit. So we probably would be somewhere in the liquid phase, right, is where we would expect our sort of CO2 to be in that case. If we looked at a minus 56.7 degrees Celsius, which is over here, and a pressure of 5.1, that would put us right there. That's the point where all three phases are in equilibrium with each other. That is our triple point, where it would be solid, liquid, and gas at that combination. So if you wanted to get your sort of dry ice into all three phases at once, you would need to get it to a temperature of minus 56.7 and a pressure of 5.1. Any questions on that there? If we bump the temperature there to 10 degrees Celsius, which I'm thinking is in this area, and 1 atmosphere, which is about here, so we just kind of go over 10-ish, 10, actually 1 atmosphere and 10 degrees Celsius, maybe in this area, that would definitely be our gas phase. That's solid, liquid, and then obviously over here is gas. So it would be in our gas phase. And let's take a look here at the last couple here. Minus 78.5 in temperature is here. And 1 atmosphere actually puts us like right on that line. And if we look at that line, that is the line between solid on that side and liquid on that side. And at 1 degree Celsius, we find ourselves right on the line. That's basically our transition point between those two. And those guys would be in equilibrium with each other. And we would have both phases occurring, solid and liquid. And lastly here, 50 degrees Celsius, which would put us past 31. And 80 atmospheres would put us way up here in this sort of past the critical point. Remember, that's where our supercritical fluid basically would be, where we have it flowing like a gas and has sort of the density of a liquid. Any questions on the phase diagram, how to use it, how to figure out phases? Any questions on any of that?
Professor, I had a quick question. For the second to last one, why is it solid and liquid and not solid and gas?
It's solid and liquid because I'm just going to I'll just draw a really bad version of that line, but basically at 1 atmosphere and what was it there? 10 minus 78.5. If we took that guy up, it actually put us right on that line, right? Is where that point would be. And kind of to the left of the line is basically the solid state. To the right of the line was, did I put liquid there? I'm sorry, that should have been, which one are we at there? I'm sorry, that should have been gas, my bad. If that's where you're asking, it actually should have been gas because that's where that is on that side of it there. So it actually should have been solid and gas in that case. And it's because it's right on the line. So it's basically that sort of transition that occurs. In this case, it would actually be the sublimation sort of idea that will be occurring at that point. So that's where that should be. I'm sorry, it was down here. So that's gas. So it definitely should be solid and gas, if that's your question. I think I wrote the wrong phase there.
Okay, thank you.
You're welcome. Other questions? Hold on. I was looking at the liquid way up here. Yeah, so obviously between solid and liquid, it would have to be way up here, you know, kind of over and on this line would be, if you landed anywhere on this line here, would be between solid and liquid. Other questions? Thank you. That definitely should be gas. Okay, so I think we'll lay it up there. I'll give you a